To start off this video, I'm going to give a brief history of chlorofluorocarbons, otherwise known as CFCs, before eventually delving deeper into their role in our society and the potential negative impacts that they have. At the most basic level, chlorofluorocarbons are non-toxic, non-flammable chemicals which, as their name suggests, contain atoms of carbon, chlorine, and fluorine. In the past, ammonia, methyl chloride, and sulfur dioxide were used as refrigerants until they were found to have a sometimes fatal effect. In response to that, CFCs were first synthesized in 1928 by Thomas Midgley Jr. of General Motors as a safer chemical replacement for refrigerators used in large commercial applications. A few years later, in 1930, the large companies DuPont and GM went on to create Freon, which is essentially just a more commonly known nickname for CFCs. For a long time, these CFCs were used in the manufacture of aerosol sprays, blowing agents for foams and packing materials, as solvents, and as refrigerants. It was a cheap, apparently harmless solution for many problems our world faced at the time. Additionally, for a long time, and even now, some CFCs are used in aircrafts as a method of putting out potential fires. Now I'm going to give some basic information about these CFCs and tell more about why they were in use and why they are no longer. So, first off, they are a subset of halocarbons, and scientists initially believed their chemical inertness made them harmless. They are non-toxic and non-flammable, and have potential lifespans of up to hundreds of years. Finally, they have very high boiling points. While these CFCs essentially made the transition to modern life possible for our species, the discovery of their negative side effects led to a huge increase in the attention given to these chemicals. In the 1970s, scientists such as Professor F. Sherwood Rowland and Dr. Mario Molina discovered these compounds break down at high altitudes in the atmosphere. The CFCs undergo photolytic decomposition due to UV radiation. This then allows the chlorine to break off from the CFCs and bond with ozone molecules. This animation gives a good physical representation of what happens during this process. The chlorine breaks off from the CFC and bonds with the ozone molecule, before a free oxygen then bonds with that one other oxygen to leave the chlorine free to go to attach to more ozone molecules. I will now do a slower walkthrough of this reaction as a whole to make it easier to see what is actually happening. The free or radical chlorine, which comes from the CFC, bonds with an ozone molecule, or O3. This then forms a chlorine monoxide molecule, ClO, and one oxygen, or O2. This chlorine monoxide, the ClO, then bonds with a single atom of oxygen to form a chlorine and an oxygen. This free chlorine can then go on to react with more ozone molecules and continue the catalytic reaction. To bring this all together, first off, the CFCs are released into the atmosphere. They then rise into the ozone layer, before the UV radiation releases the chlorine from the CFCs. This chlorine molecule then attaches to the ozone pieces and destroys the ozone layer. Due to this depleted ozone layer, more UV radiation, specifically UVB radiation, gets through the ozone layer, causing more skin cancer and other health issues with many people. In 1987, 27 nations met for the Montreal Protocol, otherwise known as the Montreal Protocol to reduce substances that deplete the ozone layer. Essentially, this meeting met in order to create legislation that would phase out the use of substances harmful to the ozone layer. It restricted the production of CFC 11, 12, 113, 114, and 115. In 1990, an amendment was made by the group that called for entire removal of CFCs by the year 2000. In 1997, the Kyoto Protocol, which is an international agreement which commits its parties by setting internationally binding emission reduction targets, was put into place. Essentially, this protocol measured the amount of CO2 emissions from each nation and placed a heavier burden on developed countries because they are much more likely to produce these CFCs. Our modern-day way of life depends on those things that CFCs allow us to accomplish. Due to these negative findings on the environmental impact of CFCs, multiple alternatives have been discovered, the first of which are HCFCs, otherwise known as hydrochlorofluorocarbons. These are better than their CFC counterparts because even though they still have the chlorine, which can cause ozone breakdown, the chemical has a much shorter lifespan overall. Another alternative are HFCs, also known as hydrofluorocarbons. These have no chlorine and as such pose less problems with concern to the ozone layer, but they are much more expensive to create. In summary, for a long time CFCs were used without a full understanding of their consequences. However, we now understand the negative impact of our use, including the ozone hole. Thirdly, a single free chlorine can destroy nearly 100,000 ozone molecules. Fourth, the entire world acted quickly to stop our destruction of the ozone layer. And fifth, due to our reliance on chemicals with uses similar to CFCs, Much more environmentally friendly replacements have been found and are being put into use as we speak. Thank you for watching. If you have any questions, I'd be happy to answer them. The next two slides are just picture URLs and source citations for the video.